so no biologists, right? Okay, so all right, no, this is important because I want to know where I'm going to start with the class. Okay, I have a plan, and I would like to discuss in like 10-15 minutes where we go and at which level I'm going to deliver the class. So last week, for those of you who were at the workshop, I delivered 3 main classes about how to use stochastic processes, partial differential equations. I went very fast because this was for professionals. So I want to know how much now I have to detail all of this in order to see how I'm going to prepare the next lectures. If I start really at the basic level of stochastic processes, or I can move on to already asymptotics and partial differential equations, and the link between PDEs and probabilities. This is what I would like to have from you, because the idea of all of this class is for you guys to have in your hands mathematical tools to be able to develop the math, and to produce ultimately papers in applied mathematics, while at the same time being able to do models, to understand how models are done, and to go into collaboration where you can extract from the biology the math at the molecular level. So you can do stochastics, analysis, simulation, data analysis. All right? So before I start to give the possible program and to see with you how we go, there are 2 books that I think are the new generation of books that go in that direction. The first one, I mean, there was this is the first of the 3 of their shoes, which is called Theory and Application of Stochastic Processes. Right? So I'll circulate the book so that you have an idea. So basically, the class aims at understanding the material here. This is the first book, and it's called An Analytical Approach. That is how you use technique from classical mathematics, asymptotics, PDEs, to solve questions in probability. Right? So let me just recapitulate for those who just arrived. My idea in this first class is to see the level at which I will do the class. You know, if you guys are all okay with stochastic processes, I can skip stochastic process, go directly to the PDE analysis. If, on the other hand, it's not clear, I prefer to spend 1 or 2 classes about explaining this slowly. I'm not going to repeat the theorems. I have decided to lose a lot of the rigor, to present to you ideas and how do you do with stochastic processes. The proofs and everything can be, in my opinion, found in your department of statistics and probability, where people are professional on this. So in order to move on to ideas and calculation, I'm not going to pay much attention about rigors. Okay? So again, from those who arrived, you're all mathematicians by training, applied mathematician, or physicist, or I mean, what is basically your background? So who is mathematicians, let's say probabilist, apply math, analysis, okay, physicists, okay, engineers, okay. So for those of you who are physicists or engineers, how much you're familiar with stochastic processes? For example, a stochastic equation, do you know what that is? Or shall I start at the level of explaining what is a stochastic equation? It's important for me, to start to see how I should start the class. For example, if I write you an equation like this, like x dot equals b of x plus sigma of x w dot. Do you know what all of this means? So now it's not clear to you. Who else? For who else is not clear? 2. Okay, 3. Okay. So then, if it's not clear for you what is a stochastic equation, I think I would like to spend at least 2 or 3 classes. So now we are going to make the plan all together so that you are satisfied. You know, I cannot satisfy everybody every day, every lessons, but at least we'll make a plan, because if you guys, you know, do not understand this, it's not worth of continuing. This is the basis of stochastic modeling. Okay, so let's make a plan for the entire class. So let me finish with this. So this is the first book that you could start reading. It shows that you don't need to know about measure theory and all of the abstract. That's mine?
Yeah.
So it's going to die soon. Yeah, okay. That's, you don't need all of the classical pathway of what people have, how people teaches stochastic processes. You can go directly, and this is my approach to the stochastic Ecole calculus, to try to understand what is the meaning of this equation, so that you can directly use this to model and to do simulations. If you do a simulations, it's a way to understand a stochastic process and the way to create the statistics. And from this, you can always, if you are interested, go back to all of this classical way of looking at it using measure theory. Okay, so I would like to have a practical approach, like more engineering or physical, but still using at question in mathematics, how you solve the equation, how you find distributions. You know, those are questions in mathematics with a practical applications. So this is the first book. Yeah, there are 3 books. One is this one. The second one is about how you use this for signal processing. And the third one, which is more like what we're going to discuss. So I'm going to, you know, the book will circulate, and there is then our book about the stochastic narrow escape. The book is divided basically in 2 parts. One is about asymptotics and explains how you go from stochastic equations to mean first passage time. So this is going to be also an important part of the class. And the second part of the book, this is about how you model at a molecular level, molecular and cellular processes. How you go from a chemical reaction to a cell behavior. Okay, so the idea is that after these few classes that we will discuss together, that you will be able to take the book and you will be able to be independent, to read the book and understand what it says. Okay, so I can, you know, for those of you, one is going this way, the other way, you can have a look, spend time, you know, looking at it while I'm talking.
Very good. When do you expect to get to the special topics, like on biology and so forth?
So this is the point of now. I'm discussing the plan of the entire class, so that you guys knows when to come and not when to come. Okay, I think this is important. So I propose, so this is the organization of the entire class. So I propose to do at least one or two, at least I will need two classes about stochastic processes. So basically is to understand what is the meaning of this equation. Let's say dx dt, this is the velocity of a trajectory, which is driven, let's say, by a vector field plus some noise. So I will explain later on in the class. So this is like a deterministic field. And and this is noise, stochastic Brownian noise. And basically with this, we can do a lot. For example, if you have a system, not one, but this lives in higher dimension, and for example, you put the noise here with a certain, sometimes it is 0, sometimes it is not 0, you know that I will explain maybe a little bit of this. There is a constructive way to generate any Markovian process with almost a given spectrum. Let me repeat. Okay, if you don't know what the spectrum is, this is the power spectrum. Is you take the square of the Fourier transform of your signal, and basically it has a certain behavior. This is called the power spectrum. And so suppose it has a decay. Let's say 1 over f to some power alpha. Can you find a stochastic equation with more or less something that is as close as you want from this power spectrum? Okay, so this has been solved 30, 40 years ago. But so what I want to say is that this contains, it is very, it is a large class of processes from which we can do a lot. Here, there is a class that maybe I will spend time on. This is called jump processes. This is continuous. So this B is a deterministic field, let's say sufficiently continuous. Let's say at least of class CK, which means sufficiently differentiable. Sigma is also a deterministic function, sufficiently differentiable. Okay, so the question is, the first two classes is, what is the meaning of this equation? When this is 0, this is purely deterministic. When it is not 0, this is deterministic plus noise. So how do you study this, right? I want to spend time, I think it's important, just to understand what is the meaning, for example, of integrating this equation. What is the meaning of integrating something which depends on noise? It was the question that 30 or 40 years ago people asked. Okay, so we do stochastic processes. So this equation, I want to spend some time. Now, this is abstract. Now, in physics, it comes from the Smoluchowski equation, from the Langevin equation, which is, so I would like to discuss then what is called the Langevin equation, which is this equation. So there is here some, we might write it alpha dot. So this is like, they call the Langevin equation. So I would like to introduce the Langevin equation. I would like to spend some time about what is called the Smoluchowski limit when gamma goes to infinity. But this equation can be basically replaced. So what is the meaning of replacing? So we have to go into the notion of convergence into an equation where you can drop the inertia. So let me remind you, this is called the Langevin equation. It has been from the classical Newton's law of motion. Acceleration equals force. But here there are two additional terms that I would like to discuss. And this is coming from the noise. Now, gamma and alpha are coefficients. V is the, let's say, a force coming from a potential. V is a potential. And so alpha and gamma are constant and they are connected. This cannot be any constant. And this is called the fluctuation dissipation theorem. And I would like to spend some time explaining why gamma is connected to alpha and how. Okay, so this I would like to take the path of Chandrasekhar in his famous article 1945. Okay, so how to study Langevin equation, one, and how to study the limit gamma goes to infinity, which is called the Smoluchowski limit. Okay, so I think this is from the stochastic processes, and I will see some example of applications in for example, I'll state the problem. I'm not solving it. Application in how a channel select ions. So you have in the membrane, you have this is a membrane. We have here some channels with some specific properties. And the question is, for an ion, how we can model ions in here. I'll state the questions. I'm not going to answer the questions. So application in cell biology, cell and molecular biology. I'll give some. So this is basically, I think, 2 classes at least, right? This is 2 classes. If we go fast, maybe I'll start even today. Okay, so then there is another class of questions. So, and also, yeah, the important part here, I would like also to discuss what is the Ecole calculus to understand what is the meaning of integrating this equation. Okay, so D is going to be Ecole calculus. Again, there are classes that where the Ecole calculus is like 40 hours. I'm not going to do 40 hours, but I give the principle of Ecole calculus and how it is used here to see if you want to integrate this. If it is a classical equation, this is clear what is integrating an equation. But here, with a term which is the noise, which I haven't discussed much, we'll have to understand what it means. Okay, so this is usually a physical approach, and this is more mathematical approach. And then there is another part, and then I would like to spend maybe 1 or 2 classes also on this. This is called the connection between the stochastic processes and the partial differential equation. So this is the derivation. I'll spend some time once we have this derivation of the Fokker-Planck equation. Fokker-Planck, mean first passage time. We can also look at the conditional exit time. Conditional exit time. And this is the formulation in terms of partial differential equation. How you derive this equation, which are PDEs, partial differential equation. So the Fokker-Planck equation is an equation for the density probability function for the variable for the stochastic processes x of t. And this is the probability to find the particle at position x plus dx, condition that the particle at 0 started at y. So this quantity, let's call it pt x and y dx, this density here satisfies what is called a partial differential equation. And it's important, the same that the mean first passage time, that is how long it takes for a process, if you think about the domain, to find any part of the boundary. So you start at position x, and you ask how long it takes in average to escape. How do you solve this question? How do you formulate this question? This can be formulated in a partial differential equation. And I would like to explain slowly how you do this. Okay, and also you can condition, this is a lot done in finance. For example, you want to know that the ensemble of trajectory that are going to escape here, suppose condition that you first hit this part of the boundary, let's call it A, before you escape in B. Right, you want to get such amount of money before, I don't know, something happened. So this is everywhere. This is in biology. This is a classical example of conditioning. So how do you formulate this? Okay, so this is formulation. So this is maybe about 2 classes. Then number 3 is how do you solve this equation? And this is very hard. In general, we don't know how to solve analytically. But, so there are two classes of problems that have been looked at, and maybe there are 10 of thousands of papers on this. And it's still, there's still work to be done because it's, they are generic. One is activation escape. So this is the, so activation through a potential barrier. This is called the Kramer's potential barrier. This is called the Kramer's problem. So this is the classical problem problem. You know that if you have a potential well, this is the classical model in chemistry, where you have a particle, and this particle has to escape through from a potential. How long it takes for this to happen? And so this is the classical picture in dimension 1. So the question is, how do you calculate the time it takes to escape? So this is like a Milford's passage time problem. But now you want to solve it. So we would like to, I will show you the formulation in dimension n. When V comes, the force here comes from a potential well. But I would like also to spend some time on the case where it's not coming from a potential well. That is, suppose you have what is called a non-conservative system. And an example is, suppose you have in dimension 2, if you have an attractor, so here basically if you have no forces, the particle, any particle located here after some times will fall off to the bottom of the well. Now, this is a deterministic picture. And why a particle is able to escape? What's the reason? What's the physical reason for this? It's because
thermal energy.
That's right, it's because of the noise. Now you want to understand how comes it happened? Is it like a big fluctuation that will kick the particle out in one shot? Or is it like an ensemble of rare events against the field that will push you out? Okay, so this is not something that is simple to understand or to analyze. And what is usually the optimal pathway? So for example, suppose you have here a limit cycle. And this limit cycle, it's an attractor. So things are rotating. This is a deterministic picture. Right? So if nothing happened, after some times, you end up here at the center. I mean, infinite time, if it's spiral here. So this, you know, that if the field has a limit cycle, it cannot be conservative field. I mean, I'm not going to discuss that now. But now we can ask the same question. How long it takes if you have a particle? So if you have a particle with some noise, with some small noise, amplitude of the noise, how long it takes for the particle to escape? So again, a type of Milford's passage time question. So how do you look at this? And this is important in stability in biology, where if you have an engineering type model, most of the time it's not conservative. Most of the time you have a non-conservative dynamical system of this type, and B is not the gradient of a potential, and still you are interested in calculating things. Okay, so this is how you calculate the time. Let's say when the noise, the size of the noise, so let's call it sigma, I'll call it now epsilon. Sigma here equals epsilon. It is small. Small means small compared to the amplitude of the drift. Not of course at zero, but let's say the amplitude. We can take, for example, the maximum amplitude in this entire region. So how tau depends on epsilon. And the Arrhenius law of chemical reaction said it is a constant C epsilon exponential U divided by epsilon. And the goal is, of course, to understand what is C epsilon, what is this term, and for which point this is true. Because if you start very close here to the boundary, it's not true, because you escape like this in one shot. So this is true, you know, for a certain ensemble of points inside. Okay, except sometimes here, which is called here, it's called a layer, which is called, this is the name, is called a boundary layer. All right, so I would like also to spend time on what is a boundary layer. And how to find this. So this is the first class of problem I would like to consider. And there's a second class of problem, which is called the narrow escape problem. It's a narrow escape problem. So the questions can be formulated very easily. You have a domain, and on this domain you have a small hole. So a particle starts at position x, and we're interested in calculating how long it takes for this particle to escape through the small hole. Right? So can we calculate the mean first passage time, tau of x? That is the time to start with the mean first passage time to a small hole, starting from x. All right, so you look at the average, and again, the question is, when epsilon is small, can we get a formula for this? And why this is important, because again, if you do a numerical calculation with something which is very small, the time will be, as your intuition tells you, it should be very long. So any computation, if you don't just put that on the computer, this will not tell us how it depends on parameters, right? Because you get a lot of variance actually from all of this. So the only way to go about this is to find an asymptotic calculation. How you calculate this in the limit epsilon small. Here epsilon represents the size of the small hole. Here epsilon represents the amplitude of the noise. All right? Two different meanings. Okay, so I think this is two classes. I think this is, again, between 2 and 3 classes. Those are classical problems. But I would like to address them using asymptotic analysis and boundary layers. Okay, so let's say if we're okay on time, this is between 2 and 3 classes. And if somebody is writing very well, I'll be happy to have a copy of this so that I can try to keep on with what I'm proposing. So 2 plus 2 is 4, so we will be here at 6, 7. Okay, so then, because I would like to connect also with data, I would like to spend maybe one class about, so it's 1, 2, 3, 4, about denoising. That is, suppose you have a stochastic process, and this process you add, let's say, some noise. So you have x, this is the physical process, and then you add here some noise. Sigma is a constant, let's say W is a Brownian motion, and suppose you're observing at a sample time y. How can you reconstruct the properties of x? Here, because of the noise, you will have corruptions. So how do you reconstruct properties of x when you can only see some partial information about y? Let's say you sample y. If it's a continuous process, you sample it, let's say, at a period of time to fix delta t. This is fixed. And then you look at it, at a certain discrete ensemble time points. You have a series that can be as long as you want. How can you reconstruct from the properties of this the properties of x? So maybe this will be one class, and this is important because this would be for the connection to the analysis of what is called super resolution microscopy, which is a big thing nowadays, to have to understand what kind of information you can extract at a nanometer, tens of nanometer resolution. So this is the reason why I'm doing this. This is for the super resolution microscopy analysis. So those of you who came last week, I've shown, again, it was very fast because it was for a professional audience about how this can be done, but I would like to go slowly, and at some point, when I need to introduce this kind of problem, I'll show data to see how to do this. So then 5, I would like to discuss an analytical theory of stochastic chemical reaction. So basically the idea of this is to understand how you can activate a cellular process from a molecular level. So basically we have here a few numbers of binding sites, and I would like to describe in different circumstances, if you inject here, let's say 10 molecules, K molecules in practice, and 10 molecules, and the molecules are moving by Brownian motion, they can bind here for some time, so they are retained, and after some time they can be released, and for example, suppose they can continue through this afterwards. For example, what's the probability, if you repeat this many times, what's the probability that you have, let's say, 5 out of 10 molecules that are bound? What's the probability that 5 out of 10 are bound? And how long, so you understand, right? So suppose at time 0 you send, let's say, a certain number of molecules. They can either bind or they can leave through here a hole. What's the probability that this happening? Or when the hole is closed, is how long do you have to wait, let's say, for a given threshold to be attained? Just 1 second, we need to start to be hot here. Okay, so this, we have called this is a theory that we have called mean time to threshold. Mean time to threshold. For example, we have used it. It looks abstract, but actually this is formulated in terms of Markov chains. And we can have 2-dimensional Markov chains. That is, you can look at the joint probability of free particle and bound ones. So then you can get Markov chains in a 2-dimensional Markov chain, and then you have to find paths in this 2-dimensional Markov chain. So this is the formulation is not that hard, but finding the probability you are interested in, formulating this can be formulated in this framework of 2-dimensional Markov chains, for example, when we have 2 independent variables. And this has many applications. And I want to spend some time on this, just to give you an example to motivate why studying this. In the nucleus, you have what is called messenger RNA. And you can have, let's say, good guys and bad guys, whatever their names, biological names, it's called microRNA, that can come here. If you have a certain number of binding sites, and if this microRNA are, let's say, bound to all of them, let's say all of them, then this is not functional. This messenger RNA can go to the garbage. Now, we're interested in the following question. Now, in addition to this bad guy, there are good guys. If this guy comes and it binds to here, then the bad guy cannot come. And this can be dynamic, that is, this binding can last for some time, so it can have binding and unbinding. So the typical question you would like to ask is that if you know the concentration of bad guy and good guys, what's the probability that this guy will leave through a small hole before being degraded by the bad guys? So this is exactly a question where you have to have, and the number of binding sites can be of the order of a few, let's say 10. So how do you calculate this? So this is a direct application for this, just to motivate why we're going to do that.
That sounds like a video game.
Yeah, if you see science this way, science for you is fun, and it should be fun. That's true. I like it. Okay, you guys understand where we are going, what we want to do? Okay. So, if I have some time, I then would like to go to what is called jump processes. Jump processes is things where you jump at a random time. Now, the analysis of jump processes is not containing all what I have described so far. So how do you analyze jump processes? It's usually very hard, but there are some approximation. For example, if you jump very fast, then you can do some approximation. Or if the size of the jump is small enough, you can also do some approximation. This is called Kramers-Moyal theory. So I would like to discuss a bit this. So jump processes, mean first passage time. So this is basically, it has been developed a lot in the 80s, 90s of last century, right? A lot, for the reason of queuing theory. And you know, queuing, you go to a favorite supermarket, there is a line, you want to know when you're going to get service. So, you know, somebody gets service, you have to wait. So the question is how long you have to wait, and it's a jump process. And so I would like to give an application on, so mean first passage time for jump processes in some limits. And I would like to give an application to what is called the telomere length. Telomere length. So very quickly, do you know, you all know that in our cells we have chromosomes. The end of the chromosomes are called the telomeres. During each division, what has been shown, and this was awarded, I think, 2 or 3 years ago, Nobel Prize from somebody from UCSF, a Blackburn, that after each division, the length of the telomeres can shorten with a certain probability, but then there is a molecule called the telomerase that if it's there, the length can increase. Okay, so if you imagine that this is the length of the telomere at n division, so at division n+1, either the length can be decreased with a certain probability, let's say, I don't know, probability p, or it can increase by v with probability 1 minus p. Suppose you give that to your computer. Yeah, what do you get in the end? What kind of distribution you get? And so an important question is, of course, when is the first time that the length gets shorter than a certain threshold? And then why it is important? Because the cells stop dividing. If it continues dividing, you know that this is linked to a kind of pathology such as cancer. So it's still unclear how this mechanism occur. And there are few models. So one model is to ask, for example, how long it takes to reach a certain threshold, how you calculate this. And suppose you have, let's say, 32 telomeres. Suppose you have 32 of them. Now you can ask statistical question about extreme case. Let's say you look every time in your simulation at the shortest. You see, you're at division n, so you look at the shortest one. So when you do the next division, maybe the shortest one is not anymore the shortest one because another guy, because maybe the shortest was increased. So if you track the shortest one, so you look at what is called extreme statistics, what can you say about the dynamics of the shortest? And usually this is interesting only to formulate the question. Even if we cannot solve it, at least we know the statistics to look at if you do a simulation. So what is called extreme statistics. Extreme statistics. For example, what is the dynamics what is the dynamic of the shortest one. Okay. So we said that for this denoising, it's about one class. Analytical, this is also one class, no more. And then germ processes, so I'll include this example in here, germ processes, one class. How many classes do we have?
What is a class?
A class is 3 hours, 2 hours and a half lecture, 2 hours lecture of Friday. This is my definition of a class. So we have, let's say, a term is about 2 months. 2 months is about 8 weeks, more or less 8-9 weeks, right? What?
I think you're over already.
I'm over? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. Anyhow, I'm going to. I had in mind more stuff. This is okay. Yeah, stochastic. Okay, I want. Yeah. There are two. Okay, we will see if you guys feel that it is too easy. I'll skip. But if you are lost after 1 or 2 classes, there is no point of me continuing. The idea is to transmit some kind of knowledge that we have acquired for the last 10, 15 years. Okay, so you let me know, tell me, David, it's too slow, we are all sleeping, or you're too fast, there's no way we are going to come back next week. Just let me know so I can go with an appropriate mean velocity.
I mean, all of the students speak for themselves, but I mean, why not, make the class as much about your specialty since you're only here for a few months, rather than spend a lot of time on the basic material. Maybe they've already seen that.
So what do you mean? That's to do to?
I mean, all these things in the end. I mean, if they don't see it with you, they may not see it in their education or some of the other things. They may be able to see in other classes. So maybe it's worth pointing.
How I can go into all of this complicated stuff if I don't discuss this narrow escape to say.
Surely topic 3, yeah.
Yeah, and also, usually it's not much taught how you go from stochastic processes to solve the PDEs. Usually in a class of stochastic processes, people present, the equations, the fact that you have a lot of Grunwald's theorem to show that everything converges, and so what? At the end, you say, okay, what am I going to do with the stochastic processes? And in physics, usually you ended up not seeing much of the hard asymptotics.
I'm expressing my selfish preference.
No. I understand. So I'm trying to satisfy. I understand your point. It's not easy to deal with because even if the spots are in books, they are not in a single book. And if you guys in the end can become independent, that is, you can open the book and understand. What it means and where you can go and ask questions to the appropriate people, this is already something. Okay, or maybe if we don't have enough time, I can also do, I can extend, we are here until June, so I can go until May, not until April. Because now it's like February, March, April. Yeah, we can go, if some people are interested, I can move on, I can continue so that you get these lectures. Okay, I'll write anyhow what I had in mind, and we'll see. The part number 7, I wanted to show you, so you see there are different classes of models. The models are derived from physics, and this is great about, what is great about molecular and cellular processes, that you can have physics with you to derive things, to write with from Brownian motion. But there is today a tremendous need of understanding all these stochastic processes and this formulation, for example, in neuroscience. How the brain works. Now, how the brain works, this is a very hard question because there are so many scales involved, from molecules to cellular to neuronal cells. So people didn't start at the molecular level to understand how a network is working. They generated a lot of engineering type models, which are good. They they are not derived from any fundamental biophysical principle, and still they are good. And how to analyze them? What those models are inside? And I think I would like to spend some time on them, especially to go, this is a multi-scale process, how you go from the central level to the network. So this is at the age of this meeting, but I think it's very instructive because it's the same. We have stochastic processes, the same kind of methodology. So I would like to present in particular what is called the model of depression facilitation for a synapse facilitation, and how this influence network properties such as oscillations. You see, suppose you have cells, none of them is an oscillator. Nothing oscillates. You put everything together, there is noise, there is some type of connections, and the ensemble oscillate. How comes? What's the properties? Let me repeat. You put cells, structure, it has no intrinsic oscillations. You connect them, they have noise and they have those properties. It turns out that this ensemble, this is what we have, what is called the pre-Botzinger complex in our brain. This is what generates the inspiratory rhythm. When we breathe, you don't think about it, but you breathe automatically. You know how many cells are responsible for this? I mean, you know how many neurons we have in the brain, right? We have about 10 to the power 11, more or less. The number of cells responsible for this is about 500. 500 cells that are doing this, and it's robust. Now we have to understand how it works. We don't want to wait 20 years, right? How it works. So this, we worked on this some years ago, and it turned out that the noise and these properties are important, and it creates this oscillation. So I think I would like to spend some time on this. Again, just by thinking about stochastic processes, having a model, how to analyze it, gives an interesting question. There is also another property which is called up and down state. This I will show you, I do a little class about neuroscience. Neuroscience, I mean the big dogma in neuroscience is that you learn bifurcation, Hodgkin-Huxley, and whatever comes from it, and that's it. You are a mathematician that know neuroscience. I would like to break this dogma. Neuroscience is not about excitability. There is much more than excitability. And I'll show you some of this aspect. Not all, I don't have the time. But for example, again, I asked last week, basic question in neuroscience are not understood. What is memory? What is the notion of keeping things in mind in our brain for years when it is encoded in some molecule that lasts days? How do you maintain something stable? So those are not questions from quantum mechanics, from quantum field theory, but are elementary questions. To that day, nobody has an answer. And it's probably very abstract, the way to answer this question. Let me say one thing. 100 years ago, a little bit more, 150 years ago, there was this notion of infection. That is, people could be infected, and nobody knew what was the reason of infection, that you get disease. So people say it is due to something that you cannot see. So if you read about history in the Academy of Science, when Louis Pasteur came and said that it should be due to something that we cannot see, people laughed at him. What nonsense are you talking about? You say that something that is smaller than what we can see can kill us? Yeah, and he explained that this is something that can enter into cell and can make all damages. So from that time, if you think about it, it was very abstract to propose something with such radical ideas. And something that you can not even see under the microscope, which is called a virus, for example, can kill us. It's very abstract. It's something that you cannot see from your instrument. You deduce it exists. And you say it has a major consequence, and he started all of this generation started to give the rules of classical hygiene. You have to wash your hands, you have to boil your food. All this came out from thinking about something that was abstract. You cannot see. So what I'm saying is that it's a continuation of trying to find ideas of things that we don't have any idea how it works, and still we would like to make prediction about how it works. To that day, nothing has changed much in terms of our way of thinking. Okay, so the idea is that I believe that through modeling stochastic processes and very clear understanding of the biology, you can make progress not only in your field of applied math, physics, but also in biology by revealing things that nobody can reveal without your understanding. This is my belief that achievement can be possible. I mean, achievement comparable to somebody that do experiments. Okay, this is my 5 minutes of ideology. Okay, so I would like to spend time on this, and this will bring us back to this question about how you escape from something which is not a vector field, which is not a gradient, and this is usually coming from this kind of questions. So why am I doing this? Because you know that there is about $3 billion in the United States and about 1 billion euros in Europe injected into neuroscience. In Europe, I don't know how much it will be successful, but it is supposed to be something computational. How to analyze neurons using what we have here to say something about the brain. So it's not that there is a demand for this, a big demand to understand it, how it works. Okay, and so let me give you some ideas of where I want to go from here. Suppose you have an ensemble of neurons, you stick an electrode, and you have a time series of your signal. This is time, and so this is the voltage, so this is a neuronal cells, neurons, this is a pipette, an electrode. You record this, and I give you long trajectories like this. So what? What can you say about this? Can you do inverse engineering problems? So for example, can you from this tell me in average what is the mean number of connections? So we need to have, of course, a model about connections for this ensemble of neurons together. What can you say from time series? Can you go from time series to spatial information? Okay, this is the type of question I'm interested in. So now it's good. I'm attracting you towards more like what I'm interested in. So this is one type of question, and I would like to spend some time based on the model where we use this escape problem. So this is question number, so this was question B. Question A was this facilitation in the oscillation. And question C is not at the molecular level. I would like to spend some time about a structure called the dendritic spine. This is where a neuron is making a synapse. And I'm interested in the electrical properties of this. So I would like to spend one class. So this, if we can do, again, I'll see how much we go, but this is one class here. Maybe one class also here. Or maybe I will group everything into one here. Maybe it's going to be only one. And then there is another class for C. And I'm interested in diffusion in a structure where the size is about here 1 micrometer. The length here is 1 micrometer. The radius is about a bit less than 1 micrometer. And we're interested, for example, in diffusion of calcium. How long it takes for calcium to escape this? Can we find the mean first passage time? How long it takes? So this is properties of diffusion. So this is one. So this is based on this, on this part 3b, to calculate narrow escape because we have a small hole, plus something with a neck. And then there is a big improvement now, because of voltage dies, but there is still a gap in the theory. It's how you model ions in this structure. So if you look at H. King Oxford and the classical equations, ions do not talk to each other. Potassium goes in, sodium, and you have chloride, but you never had chloride plus sodium that goes together. Ions are quite independent. But there is no clear theory of what is called electrodiffusion. Electrodiffusion is really about how ions are flowing into, when they flow inside the structure, how they interact together, how they generate their field, and how you can calculate from this the difference of potential when suppose you inject here current. What is the difference of potential between these 2 points? This is a problem in electricity, but here it's not a wire, it's an electrolyte, it's our neurons, it's our synapse. So there is an improvement in the last 2-3 years because of voltage guides. People can measure, from what I understand, the difference of potential between here and here at a nanometer resolution, so inside and outside, at a nanometer resolution. So this gives hope that we can see, compare the output of the electrodiffusion model with results. Why I think it's not clear how things happen, because if you, for example, do a trivial calculation and look at sodium and potassium inside the cell, it's not counterbalanced by negative charges. It's not. So you should have an excess of positive charge, and it contradicts electrostatic. You have an excess of potential of electricity, I mean of positive charge. Things should blow up. So what happened, we don't know. And I mean, I'm not satisfied by the theory so far. Now, it might be possible that the water molecules, if you have an ion, water molecule can come and can create of kind of shield that you have to account. But this is not accounted in any PNP equation. I mean, as far as I know. And this is the scale we're interested in. This is a scale not covered by the entire field of Hodgkin-Huxley and all of the variants of the associated models. And again, it has to do with narrow escape, because we have small narrow passages like we'll study here. It has to do with diffusion, it has to do with binding, because this activity here sets the synaptic transmission. It gives the synaptic weight. And the synaptic weight, the idea is that it is encoded in the geometry, in the shape. How? Nobody knows. Okay, so everybody has written more or less the plan. There is one more thing I wanted to look at, and again, maybe I will not follow the entire, or I will skip one. But there is one more thing, one more direction that my group is involved in. This is called the nucleus organization using polymer models. So next week, I'm giving a specialized talk at the Cavendish about how you use polymer model for understanding the nucleus organization. So this is part, I don't know which one we are, 7, 8. Yeah, that's why maybe I'll stay another year to finish. So polymer models for understanding, understanding the nucleus organization. So, very quickly, the nucleus of a cell. You have a cell, let's say the karyotic cell. You have the nucleus. This is the nucleus, and the nucleus contains the DNA. It's called the chromatin. It's DNA plus a lot of things around. How it is organized, we don't know. And there is a lot of now data to try to understand. For example, you take many pictures. And you look, for example, if you tag this point and if you tag this one, you look at the proximity and the statistics of this proximity here. So you ended up with matrix which can be million by million. And how you, for example, suppose I tell you, I'll give you the information about the distance between this point to that point, this point to that point. So I know the distances to all of these guys. Okay, suppose. So for each point, I know all the distances. One point, so for one point, you discretize, you have an entire line. Another point, you have you ended up with a matrix, right, of distances. How do you, if I give you this matrix, can you reconstruct when it is organized? But this is what people are trying to solve right now. It's not solved. I'm not saying we're going to solve it, but at least I would like to show you how we use polymer models to enter into this type of questions. So there are two questions that I'm interested in. It's the some aspect of the reconstruction of the chromatin organization. And the second point I'm interested in is that suppose you can tag, you can give, suppose you can give a piece of, you have a light here that is emitted by the spot on the DNA, on this spaghetti, on this polymer. Suppose you can see only this spot. You can only watch this one under the microscope. What can you reconstruct from this trajectory about the local organization of your chromatin? Okay, so this is called, so how do you do analysis, statistical analysis? So again, this is going to be analyzed through this stochastic equation. We will use this information about denoising to see how we can extract information. And go back. So, how you extract information? So, statistical information from what is called SPT, single particle trajectories. All right. So this is 1, 2, and then. Or maybe I will reverse the order, and then there are theoretical questions for the understanding, for example, about how long it takes for a polymer to loop, so which is called looping. So how long it takes? So suppose you have a polymer, how long it takes for the two ends to come in a small ball when you are in the space, so in the free space. And B, when it is confined. That is, you have a polymer, it is confined, and you would like to understand how long it takes for the two points to come together. And why this is important, because if you take any 2 points, this is go back to the first question here about the reconstruction of the chromatin organization. And now, of course, the question is, what is the right polymer model? And so the right polymer model can be inferred from point number 2. But we will start with this, with what is called Ross model. And the Ross model is basically a correlated stochastic equation where you have one bead connected by a spring to another bead. So this is bead number k, k minus 1, k plus 1. You have here a spring constant. So this guy follows this spring, which is the deterministic force, but except that the position here is stochastic, right? And each one can move with a diffusion coefficient with some noise. So this is called the classical Ross model. And you can use this to start to calculate how long it takes for a loop to be formed, what is the mean first passage time. And for this, we need to do mean first passage time in very high dimension. So that becomes a problem in spectrum of operators in very high dimension, of the spectrum of what is called the Fokker-Planck equation. And so it's possible to solve it asymptotically. Okay, I think that if we do all of this, and then I had more stuff, but I think, if we do all of this, at least, again, you raised an important question. I mean, shall we sacrifice what is in books and just go towards what is the research topic? So my answer is that the presentation I'm going to give you is not in books, or maybe in Shu's books or in our books together. But if you don't see the connection here, you need somebody else to show you the connections. So I would prefer to do that to the extent of 3-4 classes. And then for the hot, I mean for you guys that are interested in the hot stuff, no, we can count when to come. So, you know.
Sounds like April.
In April, that's right.
Sorry, March.
Yeah, March, end of March, April. This is, yeah, but if I start already, I think, you know, the students, I'm going to have a decreasing amount of people exponentially soon. Okay, so I propose we make a break. Usually I wrote 2 hours and a half. I propose to do 1 hour class, then we'll do a break of about 5-10 minutes, because I think it's important to, you know, take your time and refresh yourself. And then we'll run for 1 hour, 15 minutes. And around 4:45, it will be time to, you know, to pack our stuff. I need to leave 5 sharp because I have to pick up my kids. All right, so let's make a 5 minutes break now. Okay, that's good. But I don't have to do anything for this, right? It goes on automatically. Okay, so let's start from this stochastic equation and let's discuss what it means, and then we will move from there. Okay, so for those of you who are not familiar with this, I would say this. If we go to the infinitesimal version of this equation, it says that if you are interested in a trajectory that is x of t, is something that lives in a space, in R3, wherever you want, and it's a continuous, even continuous trajectory. You see x of t. It will be a random process, so sometimes I call it random process, I will put it a little w, all right, the classical notation. And sometimes I will remove w to express the fact that it is a realization. That is, you start from here, you generate something on your computer that goes like this, and you do another realization, so I'll indent it with w, okay? This is a classical stochastic process. So let me know, sometimes I'll put it, sometimes I will not do it. Okay, so what is the meaning of this equation? So let's think about looking at what happens between time t and t plus delta t. This is this difference, and this can be looked at b of x of t multiplied by delta t plus sigma of x of t multiplied by w of t plus delta t w of t plus delta t minus w of t. So let's go step by step. W of t, since everybody agrees that, I mean, when I ask, this is called a Brownian motion. This is called a Brownian motion. Brownian motion. The increment, so wt plus delta t minus wt, is usually thought, this is a stochastic, a Brownian variable with variance, so it will be of variance, this can always be written, I will write it this way, 2 delta t, square root 2 delta t, psi, where psi is the Brownian, it's a random variable, it's a Gaussian variable, so of mean 0 and variance 1, and then I will write it this way, 0 and 1, which means mean 0, there's no drift, mean equal to 0, and the variance is equal to 1. again, so a Brownian variable, a Gaussian variable is characterized basically by only its second moment, which is the square of this, of the expectation, right? So this is how actually you generate on the computer your Brownian increment here. So you have increment that depends on delta t. If in general you can also have, I will also write it this way, 2 delta t d, where d is a diffusion coefficient, where d is a constant, and this is called the diffusion coefficient. Diffusion coefficient. So basically, the increment of the position of the trajectories between time t and t plus delta t is due to the drift with a time scale delta t. Sigma here, so b and sigma, they are deterministic functions. They are deterministic functions, and this is just the increment. And so the infinitesimal version of this can be written this way. So again, when you see this equation written, you have to think instinctively of this, and this can be written this way. This is delta x, and the infinitesimal version is when the delta here become d. So you get, let me write it one time. So this is d of x equals d of x of t plus sigma x of t d omega or d omega t, right? And this is delta t here. So again, you can also write it this way. If we divide everything by delta t, we get dx dt. You write it this way, and here you have d omega dt. And again, we understand where it comes from. You know, when you have this, you multiply everything by delta t, and this is the meaning of this equation, which you can also write x dot. So this is again notation, x dot, and this is called w dot. So when you see this, you have to think this is the discretization version for numerical application, or this is the infinitesimal version. Now, how do you so in general, what can we say about this? What is the meaning, for example, of solving an equation? Okay, if there is no noise, what is the meaning of solving an equation? Yeah, you integrate the equation, and this is known since Cauchy. You know that if you have and this is why I skipped all the part about dynamical system. So so we understand what we are saying. If sigma is 0, we have x dot equals d of x. And this is a classical dynamical system. And already from this is already very hard to solve. We don't know how to solve it in general. There is no simple theory. That's why people looked, for example, at what happened near critical points, where you can say that you have an attractor where you're in dimension 2, so all the trajectory converges. They can also converge this way, and you can also have not only you have more of the dynamics. You can have limit cycles, you know, where trajectory comes and don't converge, but they do. Or rotations, they also what people have found 40, 50 years ago. There's a strange attractor where you can go around one part of your phase space and then switch to another part and oscillate, you know, between the two. This is called the strange attractor, you know, characterized with the Lorentz attractor. So there has been huge school about dynamical system, and it's not my goal to repeat all what people have developed. And you know, for example, what you can find most of the time when you are studying biological questions, if you have dynamical system with a parameter lambda, that is for lambda, when lambda is changing, you can have it's an attractor, and suddenly it comes into a limit cycle. You know, this kind of off-type bifurcation. But this has been well documented. So solving an equation like this means, in general, that you start with let's say an initial condition. So solving the equation, so this is, I'm not going to describe much, but for example, this is the theory of Cauchy, which say, and again, I don't want to go into this, but basically if you give an initial condition, and if this system is sufficiently regular, then you know that you can find a unique trajectory going through this point up to some times. And the most difficult part is, of course, for example, if you want to look at long time asymptotics, how things behave. And we don't know. We know that it exists, but usually we have to work on it to know how what's the behavior. All right. So then, if B is regular, and the Cauchy theory said there exists a trajectory that is a continuous function that goes from a certain interval, open interval in general, to the space you're interested in, and x of t will be your trajectory. This is a solution. But studying the limit lemma, the behavior of x of t for long time asymptotics is unknown. So the behavior of x of t for t large is usually unknown. Okay. So now we add noise. Okay, this is I'm not going to enter this, this is classical. Now we want to add noise on this. So what is the notion of solving an equation when you add noise? There is no, you can generate trajectories, right? But so the concept of probability that you all know is that you are interested in the statistics ensemble, which are characterized by what is called the probability distribution function. Okay, so this is the shift from deterministic to stochastic. That is, now we are interested in, so associated, so this is very important, the parallel I'm going to draw now, because this is the link, fundamental link between the individual description to the collective description. So to characterize the stochastic equation, stochastic dynamics, so, and we will see it is equivalent, we use the probability, so I'll write it probability density function, which is called the PDF, which is P. So what is it? This is the probability to find a particle at position, let's say y plus dy, conditioned that at 0, let's say the particle at position x. And this probability can be written as P, let's say x, y, and t. And this reads, we have to understand what we're talking about, the probability to switch from x to y in time t, and this is multiplied by dy. That's why this is the density. This is called the density. Right? So this is a characterization. So if we know P, what does it mean? It means that if you start, so suppose you have a domain, you start at position x, and you'd like to know when I'm going to switch, what's the probability that at time t, if you take a picture, your trajectory will be inside this box around y of volume or surface of volume element dy. Right? So this characterize fully, and we'll see when we'll do the Fokker-Planck equation, this characterize fully the dynamics. However, we are not much, we haven't win much if we don't know how to calculate this. How do you calculate the probability distribution function? Most of the time we don't know. So a hard question is how to calculate, how to compute. First of all, we have to derive the equation. How to compute the probability distribution function. So most of the time we can't, nobody knows, and that's why people are using simulations or asymptotics. You see, the idea is that if the particle cannot escape the domain, you understand that this is a hard question because the geometry of the domain is important. If your particle, if the domain is very narrow or very big, it will affect the probability to find the particle here. So if it depends on the geometry, then that's why you need to use here partial differential equations. It's not something that we can escape from. Okay? So this is an important point. Now, let's move on to the idea of integrating. So why, again, I'm showing you all of this, because I would like you to connect and not be afraid to look at the tau calculation and all the properties that people have derived, because they are very important. You should look at this as a background. So we'll see later how to calculate this. Now the question is how to integrate. What is the meaning? What is the meaning? What is the meaning of integrating equation 1? This is equation 1. So for this, if we just do what you want to do, you just take delta t over there and you integrate. So we would like to make sense of x of t minus x0. And we would like to say this is the integration from 0 to t of b of x of s ds plus integration from 0 to t of sigma of x of s d omega of s. Okay, so what is the meaning of this? I just integrate formally. So if you think about something in dimension 1, if you have a deterministic term here multiplied by ds, this is a classical integral. Think about Riemann integral. Now the question is, what is this? What is this term here? What is the meaning of integrating something with respect to a Brownian motion? So the same way as the Riemann integrals has been developed by using the sums, when you cut an interval into pieces, we'll do the same here. And the question is what we'll get, and this is called the stochastic integral. That's it. So is this all of this completely new for everybody? Is it too easy, or shall I go faster? Or it's a good speed and people and it's okay? Yeah? Okay. So I'll go step by step for you to see the different step of understanding that. All right? Okay. So now I would like to introduce, this is the first and the last class, I'm going to introduce spaces, like abstract spaces, to understand what is the meaning of integrating with respect to this Brownian. And again, I do that so that you should not be afraid to look in the math literature, so that you get all kinds of properties you are interested in, and you understand what this literature can bring you, how it can help, or maybe that you are wasting your time. But it is important to understand it, to have this knowledge, to see. Most of the time there are very interesting properties in the math literature, and you need to see if it's suitable for you or not. Okay, so for this, if you decompose, if you have no, so what I'm going to do now, I will decompose the interval 0t, go from 0 to t. And now you slice it. T t1, t2 up to tn minus 1, tn. And let's say this is over time, it's unimportant that it's fixed, but let's suppose this is delta t. So you have tn equals t, which is n times delta t, right? So we cut all of these intervals, and we would like to decompose this and make the integration on each of these sub-segments. So basically, if sigma is 1 here, what is the meaning of this integral? So we can look at it as a sum of omega tk plus 1 minus omega tk, and this is for k from 0 to n minus 1. If you replace this by these sums and you look at the limit when delta t goes to 0, you'll get a sum that should be studied. Again, so what I did, I take this part here, I suppose sigma is 1. I said I would like to calculate the integral from 0 to t as a classical integral where you use the Riemann sum. So Riemann sum is what? You have, suppose you have a function, right? You just look at your square here. You can approximate it. There's many ways to approximate it. You take the approximation by the square, you let the square goes to 0, and delta t goes to 0. You have a sum that converges to infinity, and it should converge to the area. This is the classical construction of the Riemann integral. So what I'm saying is that we're going to do the same here. We're going to look, except that we don't have here a deterministic function. We have a stochastic function, right? But so we still have the sum of Brownian variables which are independently distributed. And we would like to study the sum in general when we'll have then a function here. So for this, I'm going to show you a framework, a frame to study this integral here through this calculation. So I'm going to introduce what is called the space of non-anticipating functions. So again, I'm doing all of this because I think it's important. It's maybe the part that is the most heavy part in terms of analysis of the class, but I think, again, this is what we have to discuss. So this is the space of functions that are stochastic processes such that the f omega t, this function is independent of the increment of omega of t plus s minus omega t for all positive s. For all s positive. Basically, what that means is that this point at a time fixed time t doesn't depend on any stochastic variation of the future. That is, this is independent of what happened for the future. That is for all this increment. So this is the increment. For example, if you think about s as delta t, a small increment, this should be independent of this. That is, I consider all the class of function continuous. So this is independent of this. And this translates, how do you write it in terms of probability? What is the meaning of these words in mathematical symbols? To be independent means that if you average all of this increment with the weight of this function, what does it give? I'm sorry?
The product.
The product, and the product is?
Decomposes.
Yeah, yeah, and since what is the expectation of this Brownian motion? What is the mean? 0, that's it. So this means that the expectation of f omega t, I'm going to write it once, so you understand how this translates mathematically. You all know what is the meaning of, this is a symbol of expectation, your average over realization. Your average over this little omega. So the fact that it is independent can be written the following way. This is f omega t expectation multiplied by the expectation of omega t plus s minus omega t. Why? So whatever okay, there is one more thing that I have to tell you, is that this ensemble of function has to have a finite energy. So I'm going to just in 1 second to give you another condition, but suppose this is finite, this is not infinite, this is finite. Then the expectation of this, if this is a Gaussian of mean 0, because the mean is 0 for this expectation, this is S, I call it delta t, since the mean is 0, the mean of this is 0, so all of this is 0. Okay? So this is, and the space I'm interested in is going to call H2 of 0t. This is the space of all the function f in this ensemble S, such that the energy, the integral, let's say from 0 to t, of the expectation of f omega square of S ds, this is finite. Right? So this is the space of functions such that they have a finite, so expectation of this is a deterministic quantity, which is integration from 0 to t, it is finite, doesn't blow up. And now if we would like to calculate for this space of function, I would like to give a sense, make sense, for calculating this integral. We're just putting a framework to say when we can calculate this. When this makes sense to be calculated. And we will see that when we have a function like this is okay, it falls into this result, into this framework. Okay, so now let's do this calculation for a function f that are piecewise constant. So I suppose I take a function f, which is piecewise constant. What does it mean? It means that if I take the interval 0t, the interval that we have here, sometimes I call it little t or capital T, it's the same t. And now suppose it is piecewise constant, that is you cut it, you slice it, and you have a function that is constant on each pieces. And so it's the function f restricted to the interval tk plus 1 is equal, let's say, to a constant fk. And this fk, we can call it fk of omega. It can be a random variable. It's not necessarily a variable deterministic function, right? Each time you have a realization, you have another number. But once you have a realization, this is fixed. So you have, this is, for example, f1, f2. So think about it like, and so now I'm going to tell you that the integration from 0 to t of f omega of s d omega of s, I'm going to show you this approximation and show you that it works. That is, if we then look at different type of discretization, it will work for a general function that is not necessarily piecewise constant. So you have a function, it is piecewise constant, and let's say that for this function, f, we look at, so this is tk plus 1. So for this interval, this is fk, and now this is omega at point tk plus 1 minus omega of tk. And we have to sum from 1 to n. Okay? So I will have the notation that omega k is omega of tk. So what can we say about the expectation of this integral? That is the expectation of this, of all of this equals, equal the expectation of all of this. And by definition, because of this increment is independent, this is exactly what we have written here. The expectation here is the sum of the expectation of the product, which I'm not going to rewrite. Okay, I will write it now. Fk, and this is put it here. This is 0, so this is 0. And now, this is me again. Yeah, so it has. And now, what is the expectation of the square? Now, if I take the integral from 0 to t of f omega of s d omega square. I put a square here. What is it? Okay, we have to see that this squared is, I just calculate this square, right? And so let me write it here. This is the expectation of the sum for k, the sum for q of fk f q of d omega k d omega q, where by definition omega k d omega k is omega tk plus 1 minus omega tk. So what is the expectation of all of this? Using the same property of the fact that fk is independent of this, I can take this expectation, take the expectation here of this product, multiply by the expectation of the product d omega k, d omega q. Now what is the expectation of the product of d omega k, d omega q? So for this, we have to remember that the increment d omega k, d omega q are all independent. So if omega k is if k is different than q, since they are all independent, then this product, the expectation of this product is 0, except when k equals to q, because then we have exactly this squared. And if we have this squared, so let me put it here. If you have this squared, this is this squared. And now we have to take the expectation of this, which is the expectation of this. And what is the expectation? So, what is the expectation now of, so 2, yeah, I can put it out for the expectation, it's deterministic number, delta t also, d also, and you get what? You get expectation of psi squared. Now what is the expectation, what is this? This is simply the variance, and the variance is equal to 1. So this is just 2d delta t. So this is simply 2, so 2d, what is delta t here? This is exactly tk plus 1 minus tk, multiply, so maybe here, wait, there's a factor 2. Yeah, maybe here we have to take variance 1/2. I take this variance 1/2 here so that I can get rid of, take the d omega k, let me decide that the diffusion coefficient here is 1/2 here. So that d multiplied by 2 is 1. So then what you get from here is a sum of expectation of fk squared tk plus 1 minus tk, and for k going from 1 to n. And now what is this? Expectation of a function. This is a deterministic function. Tk plus 1 minus tk, this is a decomposition of your interval. So when t goes to infinity, if the delta t goes to 0, this is the classical Riemann integral. So this converges as n goes to infinity to the integral from 0 to t, capital T, of expectation of s square ds. And by definition, since I am in the space where this is finite, this is convergence exists. And again, I'm not going to all the proofs. This is to understand that to calculate this quantity, we cut. So we did it for the piecewise constant function. And now I'm not going to prove more theorem, I'm going to state it, however. So for a general continuous function, so now if you have a general continuous function, so for any function f in the space h to 0t, so this is any function of this, there exists a sequence of piecewise constant functions. So this is an ensemble of functions such that this function converge in the L2 to f. So what does it mean? That is that fn minus f in the norm h to 0t, this converges to 0 when n goes to infinity. That is, take any function of this space. For any function of this space, you can always you cut in n steps. You approximate the value of this. It's a continuous function, so you can approximate here by the classical, constant value of the classical Riemann, which I'm not going to do. And you can prove, which I'm not proving here, that any of these functions, there is a sequence. As n goes to infinity, so you can refine here your step, converges to f in the sense that the norm defined here by this space here, which is h2 norm, I'm sorry, this means here, this is the meaning of this is f of norm. This is a norm here. So f omega minus f means you take the expectation of the difference of the function minus the limit, and you square it, right? And so in that case, for all this function like this, we can extend the stochastic integral f of s d omega of s as the limit of the integration from 0 to t of this family of functions that will converge almost everywhere, and more important in this H202 norm, d omega s. So we have extended the stochastic integral for any piecewise constant function to any continuous function, which are not necessarily constant. Alright, so this is the limit when n goes to infinity. Okay, so this gives us definitions, and so we can show, you can prove, right, that for any, this doesn't depend on the, on the slicing that you are doing. Any kind of slicing will work. You go to this limit. So this proof can be shown. It is given in the classical book of Ito Makin. So this is given in the classical book of Ito Makin. 19, this is in Springer, 1969. That's why I'm not going to redo it. This is classical. But I wanted to show you all of these steps so you understand what we're talking about, and more important, that what is the meaning of not making this integration sign here. It means that we go to the limit and we are manipulating here a stochastic process. Okay, so yeah, we have time. Now I'm going to move on. And I would like to, now we have discussed all of this, I would like to introduce the Langevin equation. Now we understand what is the meaning of integration. Now we can discuss about stochastic equation, and we can go to their integrations. And now I would like to introduce the Langevin equation and the Chandrasekhar approach, which again, we're going to repeat some of this here, but that's fine, so that you understand what we're going. And in addition, we will prove what is called the fluctuation dissipation theorem. Okay, so I want to do that now, and then we will be able to stop, I think, because this will be for next week. And next week, I'll discuss, I'll go back then to the Ito calculus. So next week, I'm going to show you, so keep that in mind. We'll do a little break in this direction, but next week, I'll show you the Ito calculus and the difference for those of you who have never seen that. If you have two stochastic processes like this, let's say x1 and x2, which satisfy a stochastic equation, then the product D, the same D that we have understood and seen here, this, if x1 and x2 are deterministic function, you know that dx1 x2 is x1 dx2 plus x2 dx1. Right? This is what you have learned in the elementary calculation. So we see that this is wrong. This is not true anymore, and it comes from this calculation. And the term that is here, the new term, is very important for the calculation of the mean first passage time and the Fokker-Planck equation. This is this difference that comes from this calculation. That's why I want to spend, sometimes to make sure that you all understand this. So this is for next week. Now I would like to make a little break in this direction, and I would like to discuss now the Langevin equation. Okay, so this approach is has been the one used by a great physicist called Chandrasekhar, and this is summarized in his very classical and very important review, The Review of Modern Physics, in 1945. So I would like to discuss the Langevin equation, which is again the basis of using stochastic processes in biology to understand how particles are moving. So the Langevin equation. So basically we are interested in understanding how a bead, a particle, is moving, let's say, in a gas. Later on, if it's more dense, it can be called a fluid. But let's start with the gas. So you have a particle, x of t, and the question is how this particle is moving when it is responding to beads that are reflected. So you embed this into a gas of particle. The particles are moving. If nothing happened, it has some velocity, which we're going to describe in a second, the distribution of those velocities. It hit the particle, and then it is reflected according to the classical, let's say, Snell-Descartes reflection. The particle reflects. And so the question is, what's the motion of this bead? So now I'll give you the assumption about the medium, because this is important to understand this. Let's make an assumption that the medium is homogeneous. this medium. For example, if we are close to a wall, might not be necessarily correct what I'm saying. Or if, for example, you have beads, heterogeneous beads of different sizes, for example, that will, of different velocities, with create some heterogeneities. What I'm going to say is not going to be true. So we need some kind of homogenization that each force that hits the bead, they are all independent forces due to this collision. So when you have a jump in the velocity, this is like what? A jump, a difference in velocity in the classical Newton's equation, this is like a force. All right, so I would like to have an assumption is all the forces here are all independent. This force is independent from this one because it is done by particles that have no relationship. So forces on the bead are independent. Right, and the fact that they are independent can be translated into the fact that in average there is the same quantity of collision from the left, from the right, from the top, from any plane, right? So in average, so according to this description, the expectation when you average all of the forces exerted on the bead, it is 0. So this is how it translates. Okay, so now what was the idea? If you start, so let me recall the classical Newton's equation says that if you have a mass of a particle and the acceleration is directly connected to the force applied to the particle. This is Newton. And we are back 300 years in time. So this is Newton's law of motion. And now we need another assumption, is that there is a drag force. That is, when the particles start to move with a deterministic speed in this ensemble, it will be stopped because of the particles that are colliding. And this drag force, we're going to assume, this is an assumption, that it is proportional to the velocity. So we have this drag force that you have in the fluid, which is proportional with a constant, gamma, velocity. There are models where you don't have just proportionality, it can be more complicated, it can be nonlinear. Okay, so then, which means that, so now let's assume I will not drive, I put the mass equals to 1, so the Newton's law of motion is like dv dt equals this drag force minus gamma f plus all the collision. So this is like a term that is the consequence on the velocity of the bead plus the forces which are the collision forces. Right, that occurs on the beads in all directions. And I'm neglecting all kind of other forces, electrostatic, gravitations. This is the basic approach.
Sorry, so what's the last form of the force?
Collision. This is the collision that I've described here.
Okay.
The collisions is the description of the force on the bead that are all independent. Okay, so we have this drag, we have this collision, and we said that according to this equation of motion of Newton's law, this is the what we have, and what we would like to do is to understand what is, can we say more specifically what are the collision if we assume that we have a gas of particles that are colliding, and then what is the probability to find the particle, let's say, here. At position y at time t. How do we calculate this probability? Okay, this is a mission of 20 minutes that we are left. All right, and then you'll have time it will be time to rest. Okay, so now you embed this into a gas of particles. What is the description of the statistics of a gas of particle? What is the big name? The guy who committed suicide. That's right. You know the story of Boltzmann. Nobody believed what he said. Could not cope with all of this. So he killed himself. He was probably 10, 20 years advanced below his time. You know, he understood that the physics could be understood in terms of these collisions of particles, while everybody was thinking thermodynamics. Okay, so what Boltzmann said? He said that the probability, okay, let's first write the general concept. The probability that the particle will have a velocity, let's say, that belongs to the space of velocity, condition that, let's say, V0 equals V0. This can be written in the space of velocity as the probability to switch from V0 to V during it. So you integrate dV. This is the probability that you change from a certain velocity. You start at 0, let's say with a velocity V0. You ended up at time t with a certain set. So I'm not here in the space, real space, I'm in space of velocity. This is the real space. And so in here, you see, you can have the velocity. So you have the distribution of possible velocity. You can do this, different direction. And this is dV. Now, we know that this what is this? Let's look at this more closely. What's the probability distribution when t goes to 0 of this probability density function? If t goes to 0, the velocity should be equal to V0. So then we are left with, this is delta Dirac of V minus V0. What is the limit of pt of V and V0 when t goes to infinity? I'll go to the other direction now. It should, the particle, you wait, so it should be embedded into all of these particles that collide all the time. And what, how do you characterize this? Now you need to look at the statistical properties of the ensemble. If you wait sufficiently long enough, so you lose track of the particle. And the particle, even if you pushed very strongly, at some point the initial push of the particle should not be important compared to all the collisions. So the memory of the initial kick should be forgotten. Yeah, this is the classical statistical physics. And then what's the distribution of velocity? It is
one divided
I'm sorry?
1 divided
1.
No,
The velocity, what's the Boltzmann said? The Boltzmann said that it should be distributed according to the Boltzmann distribution. You've seen that in the past? So what's the Boltzmann distribution? It's simply the exponential. I mean, there is a factor here. So this is, if we're in dimension 3, this is associated with the dimension. I'm not going to live in dimension 4 or 5, right? People interested in biology. And dimension 3 is good, and dimension 2 and 3 are important because what happened on the membrane. And we'll see dimension 2, there is specific behavior. Okay, I'll do it in dimension 3. So this is m divided by 2 pi kb k Boltzmann t. So this is where the t here, temperature, connect to the statistical property of our ensemble to the power 3/2 exponential of minus mv squared. I think there is 2 here, which is missing here. 2 kbt. kbt. M is the mass, so here it's m equals 1. So sometimes I write m equals 1, sometimes I leave it m. V, this is velocities, so they are distributed. So this is a distribution, a function of V. So the probability, if you are interested in this quantity, we have to plug this into here, and we get this quantity. But the idea, it's important to understand here. We are connecting here the motion individual particle to statistical quantity, the temperature. Temperature is the key. You know, that's a statistical quantity. This is a quantity that represents the behavior of an ensemble. Okay, so now I'm going to connect quantity, which is represent an ensemble, with behavior of a single particle. That is, out of all of this, you look at one of them. Okay? So now let's start to do the, so now we have this. This is the behavior, assuming that we have this behavior of Boltzmann, right? We have a bath, of thermalized bath. If there is a gradient of temperature, this is wrong, because gradient of temperature means that you don't have a uniform temperature. Assume temperature is fixed. Now, I would like to get information about the collision term, and how this collision term can be expressed in more specifically. We know that there are independent particles, so the expectation according to the statistics here is 0. And now to get more insight, we're going just to integrate this equation. How do we integrate this? So all of this part that I'm going through here, I think corresponds to the 61st pages of the book of Schuss, plus the article of Chandrasekhar of 1945. I mean, this is taken from there. Why? Because this is very good. The presentation and the ideas putting together was very, he did a very great job on this. So, how do you integrate this equation? You multiply everything by exponential gamma t, v, and if you differentiate this with respect to time, this is equal to exponential gamma t multiplied by v dot, plus gamma v, right? And this equal to this, so this is this plus this equals to f collision, which depends on the time, exponential gamma t. So now we can integrate this the way we have discussed the integration. So this is exponential gamma t v, the v of t, minus what happened at 0. So this is 0, this is minus v of 0. This is the integral from 0 to t of f collision s exponential gamma s ds. Okay? So now let's understand. I multiply now everything by exponential minus gamma t. So I multiply here by exponential minus gamma t. So I remove it from here, and I add it here, exponential gamma t is minus. So what is the limit of this term when t goes to infinity? This is by definition, this is v0, this is finite, exponential gamma t, d goes to infinity, goes to 0, right? So basically this is what we said after some times, v of t, the velocities, only depends on the collision term multiplied by a kernel, which is exponential gamma s minus t. This is an important kernel, it's called the kernel here associated to the lack of the initial velocity. All right? So now, so this is what we have. Now, how can we calculate this term? If those are random variable, independently distributed, and so the idea is that they are falling exactly into the set of non-anticipating function, which was just written over here. That is, what happened here doesn't depend on what happened in the future, on this increment of omega t plus t, t plus s minus omega t. So let's write it this way. Suppose we go from 0 to t, and we chop it into pieces. Then we get in here, this is sum of exponential minus gamma t plus gamma k delta t, f of k delta t multiplied by delta t. So I discretize this integral. This is sum of k, and I assume that each part here is on the same beam, which is a fixed delta t. And you integrate from 1 to n. Now, I'm going to set, so this framework, saying that finally, if we have independent, if you get this independent sum of collisions, you can write it, this is d omega k equals f of k delta t multiplied by delta t. So I call all of this term d omega k. By definition, we say that f of k delta t, because this is independent, the expectation of this is 0. So, and then, since we have a sum of collisions, f represents a sum of collision, we know that a sum, so there is maybe a theorem here of large number to invoke, is that the sum of independently distributed variable converges, whatever the sense of converging here, to a Gaussian process when the mean is 0. And so what we can write here is that d omega k is a Brownian motion with a diffusion term, which I'm going to call 2q delta t. We know that d omega k can always be written this way. And q here is unknown. And I would like to define and to understand what q is. Okay, and so for this, what we need is to link what we said before, the motion of a particle with the velocity. And so we need, what is the, we can calculate from this distribution, we can calculate the mean velocity. And we can calculate from this also the mean velocity. Because, I mean, the mean squared velocity, because the mean here, as we are going to see, is what? Is 0, because it doesn't move in average. But so that's why we need to calculate v squared expectation of this. What is this equal to? So remember, we're in dimension 3, so there is x, y, and z. So I usually make a lot of this like here, x, y, and z, and they are all independent. X is independent of y, independent of z, so it's 3 times basically in x. So this is 3 times the expectation, let's say, if you are only in one direction. So we can just go back to dimension 1. So this, how do you calculate this? This is calculated from here, because you can calculate at equilibrium when t goes to infinity. So I'm interested in calculating this term, the limit when t goes to infinity of the expectation of this, which is 3 times the expectation of 3 times the limit when t goes to infinity of this. And now I would like to calculate this using this infinite probability density function. So this is just v squared p infinity of v, which is independent of the initial position. And then we have to integrate over the space of velocity in dimension 3. So this will give you the result. This you can calculate, you multiply v, you integrate over a ball in R3. This is elementary calculations. And you end up with a Gaussian integral, you integrate by parts, right? And you get 3 kBt divided by m. Okay, so this is one calculation. Again, this is integrated over R3. because velocity lives in R3. And the 3 comes from here, and yeah, I don't know why I did this reduction, but okay, this is the result. Now, there's another way to calculate V, is to use this integral. So Vt equals V0 exponential minus gamma t plus integration from 0 to t of f collision of s exponential of gamma of minus t minus s ds squared. So I do this. Square. So square, okay, let me do all the calculation now. So this is squared plus twice V0 exponential minus gamma t plus integration from 0 to t of f of s exponential minus gamma t minus s squared. Okay, and now I take the expectation of everything. Expectation of this is 1 because there is no, everything is deterministic here. So here we ended up with having 2, expectation of all of this, plus the expectation of this. So now, and we're interested in taking the limit when t goes to infinity of all of this. So I'm taking now the limit here when t goes to infinity. What is the limit when t goes to infinity of this term? 0, because exponential, this is 0. What is the expectation of this term? 0, because expectation of the integral is the expectation of this term, and this is deterministic, and expectation of s by definition, it was written, yeah, it's still there, it is 0. So this is everything is 0. Now what we need is to calculate the limit when t goes to infinity of this integral. Okay? 5 more minutes and we are done. And so this you can do the same way as we did before. This is the integral, so we can slice it. I'll do it one more time. I slice f of s between 0 and t, so that this integral is f of k delta t exponential minus gamma t plus gamma k delta t, and then we have to make it square, right? So square is the sum for k and q of f of q delta t multiplied by this, multiplied by exponential gamma t plus gamma q delta t. So this, all of this term is equal to this one. This is equal to this. You agree? I didn't make any mistake. And so, yeah, so clearly the gamma 2, and so we have exponential gamma, this is the same term. If I take the expectation, this is a deterministic term. This, by definition, when I take the expectation, everything will be 0 because we have f, and I have forgotten here delta, I have delta t twice, right? No. D omega, yeah, I have d, yeah, that's it. No, this is delta t twice, but f delta t, since f delta t is d omega k here, so I put one delta t in here, another delta t in here, and this is d omega k, d omega q, exponential 2 gamma t, exponential gamma k delta t plus gamma q delta t, and the expectation of this k and q. And now this is 0 by definition, except when k equals q. So I can put it here, square, k equals q. K equals q, which means here twice. And this is simply, this is simply tk plus 1, I mean delta t, sum, okay, exponential minus 2 gamma t, exponential 2 gamma k delta t. And this, when t goes to, delta t goes to 0 and k goes to infinity, there is here factor 2. This is exponential minus 2 gamma t, integration from 0 to t of exponential 2 gamma s ds. All right, and this can be integrated into exponential minus 2 gamma t, exponential 2 gamma t minus 1 divided by 2 gamma. Now we're almost there. When t goes to infinity, this multiplied by this is exactly 1. This multiplied by this goes to 0, and we get 1 divided by 2 gamma.
I think we lost the Q somewhere.
What?
We lost the Q.
We lost the q? Yeah, that's true. We lost the q, that's very good. So it's 2q, yeah. So this is here, we have, I forgot 2q here. Because expectation of this is 2q delta t. So we have 2q delta t, thanks. And so here we have 2q divided by 2q. So 2 and 2 goes. And this calculation is almost, yeah, no, this is correct for a velocity which lives in dimension 1. Because here this is for, let's say, v of x. So we end up here having q divided by gamma. So now we have, from one shot, where it's written, yes, this is 3 kBt divided by m, and here we'll have, this is only for dimension 1, I did it, on 1 dimension, so if we're in 3 dimension, I did x, y, and z, so it's 3 times q divided by gamma, so this is the final result. 3q divided by gamma, which is the result of all of this calculation coming from the limit of this, 3 times this, because x, y, and z, should be equal to 3 times kBt divided by m. 3 and 3 goes away, so q is equal to kBt divided by m multiplied by gamma. And finally, let's write back the equation that we had here before. We had dv dt, so m, or v dot plus gamma v equals f. Now we have f, which is d omega divided by dt. So this is d omega divided by dt, which I put the limit, I'll call it omega dot. Omega dot has a variance 2q. So if now this omega has a variance 1, what do I need here so I want not to write it something with variance 1. It's another Brownian motion. What do I need to pull out from this? Square root, that's right, square root of 2q. What is square root of 2q? This is square root of 2 multiplied by q. What is q equal to? This is kBt divided by 2 kBt gamma. I don't know why there is m here. Yeah, okay, there is m because there's no more m here. Okay, let me do m equals 1. So because this is for my kBt. So here, this is very important what you are seeing here, because this is the form of what is called the fluctuation dissipation, and then I have to stop in a second, of the fluctuation dissipation theorem. This is very important, because this is the basis of many analyses of single particle trajectory, that you have the gamma here, the viscosity, And here we have square root of gamma. Square root of gamma. So this, the fact that you have gamma here and square root of gamma, this is called this is the essence of fluctuation dissipation theorem that we have reproved here using all of this analysis, like that if you have a particle, if this particle is living in an equilibrium ensemble of particles, then if you use this Boltzmann as we did, we connected the behavior of the ensemble to the behavior of a single particle, and then necessarily we found this relationship. If you don't have the fluctuation dissipation theorem, then you don't have necessarily this distribution. That's why when you are going to analyze data on the surface of molecule moving on the surface of the cell, if there is some coarse graining, for example, there is additional effect, for example, you have obstacles that remove the homogeneity, you should not look something of this type. You should look at something more general, is drift plus noise. Okay, in general, if you look at stochastic equation, they do not share this. They are written in general, drift plus noise. Only when you have embedded with the physics, you have this connection. Am I clear? Okay. Next week, you'll tell me if I'm going too fast, if it's too slow, if it's too elementary, or if it's okay. If it's okay, I'll move like this to make sure that you got all the steps before I go to the nice stuff connecting to biology. Okay? Now I have to rush.